Okay, on this video we are going to solve a problem of the Newton's cooling or warming model. So let me read the problem. A cake is removed from the oven and the oven has a temperature of 300 degrees Fahrenheit. So let me remark that. Okay, 3 minutes later it measures 200 degrees Fahrenheit. I assume it's going to be the cake. The room's temperature T ambient is equal to 70 degrees Fahrenheit. Okay, so what I'm going to do is to make a plot of the timeline of the events. So the time, the temperature, and when it says that when it is removed, the oven temperature is 300 degrees, so I assume that the cake has the same temperature. So here then this is going to be 300 degrees Fahrenheit, okay? And then it says that 3 minutes later it says that it is measuring 200 degrees Fahrenheit. So it's at this point. Okay, so what happens there is that it started from here and is going to go down. Okay, now the ambient temperature says that it is 70 degrees Fahrenheit. Okay, so 70 degrees Fahrenheit, let's assume it is somewhere here. Okay, so that is the asymptote, the limit. So I assume that this is going to go somewhere like this. Okay, now inciso A. How long it will take to cool to 100 degrees Fahrenheit? Okay, so what they're asking is about this point, somewhere here, because it's 300 degrees, 200 degrees, so I assume that somewhere here is 100 degrees Fahrenheit. And they are asking what is that time, okay? Also, they are asking about what will be the temperature after 5 minutes. So it could be somewhere here or somewhere there. But they are giving us the time, 5 minutes, and they want to have what will be the temperature after 5 minutes. So again, this is inciso A, and this is inciso B. Now, inciso C is saying when the cake temperature will be 70 degrees Fahrenheit. Now, pay attention to this 70 degrees Fahrenheit because that is actually the same as the ambient temperature. Okay, I'm going to answer that question later, but let's focus on the model. So the model solution is the temperature as a function of time is equal to C exponential of KT plus the T ambient. I'm going to replace the T ambient is 70 degrees Fahrenheit. I'm going to avoid the units. Okay, now because we have two initial conditions, and why we have two initial conditions? The first initial condition is T of 0 is equal to 300 and T of 3 is equal to 200 degrees. Okay, so we are given two initial conditions because we have two constants. The first constant is from the integral when solving the differential equation, and the other constant is the K of the proportionality, and that is the heat transfer proportionality. Okay, so let's solve this problem. Okay, so let's replace the first one, T of 0 is equal to C exponential of 0 plus 70 equal to 300. Okay, exponential of 0 happens to be 1, so the constant C is just 300 minus 70, so that is equal to 230. Okay, so my model is T of T is equal to the constant 230 exponential of KT plus the 70. Now the other initial condition, T of 0, T of 3 is equal to 230 exponential of K times 3, that is the time, plus 70 equal to 200. Okay, so what we have to clear is the K, despejar la K. Okay, so exponential of 3K is equal to what? 70 to the other side, 200 minus 70 is going to be 130. 130 divided by 230. this goes as a division. And we have to clear that k. So we can cancel 1, 0. And let's apply the natural lorem to cancel the exponential. So the natural lorem of exponential of 3k is equal to the natural lorem of 13 over 23. So this and this cancel. So you can see what is the value of k. K is equal to the natural lorem of 13 over 23, and that divided by 3. Very ugly number because it has a lot of 3's. Okay, so that is the value of the k. So the model is something like this. T of t is equal to the constant 230. Sorry, here. 230 exponential of the natural lorem of 13 over 23 divided by 3, the time, plus 70. Okay, so we have the personalized model. So what we have done here is taking the general solution, which is the general differential equation solution, and we have now the personalized model or the specific solution. A specific for the characteristic of this cake that is cooling. Okay, now let's answer the question. How long it will take to cool to 100 degrees Fahrenheit? Okay, I'm going to answer first the inciso A. Is the easiest because you are given the time and then you calculate the value of the temperature. So let's do inciso B first. So inciso B is you just replace the value of 5. So the temperature is going to be T of 5 is equal to 230 exponential of the natural lorem of 13 over 23 divided by 3, and then here the 5 plus 70. Let's do that quickly in the calculator. I am writing very small letters because the problem is it seems to be long. Okay, so let's do this. Okay, this is approximately 158.8 degrees Fahrenheit. So that is inciso B. So after 5 minutes, then it is 158. Actually, then my plot is wrong because I'm looking for the 100 degrees. So the answer in inciso A must be bigger than 5 minutes. So this temperature here is 158, and then later it is going to be 100 degrees Fahrenheit. So this plot is wrong, but we at the beginning we didn't know if it was going to be correct or incorrect. Okay, so now what I know is from inciso A that the time must be bigger than 5 minutes. Okay, now let's do for inciso B. Inciso B, what we have to do on inciso B is that they are giving us the inciso A is that they are giving us the temperature and we have to calculate the time. So what we have to do is to replace the temperature here, 100 equal to 230 exponential of the natural lorem of 13 over 23 divided by 3, the time, plus 70. And from there we have to clear the time. Now this is inside the exponential. Okay, the exponential. So okay, so let's clear the value. Okay, so this 72, the other side is going to be 30 equal to 230. Let's make the division, divide by 230 equal to the exponential of the natural lorem of 13 over 23 that's over 3, and then the time. Okay, we can cancel a 0. 3 over 23, we cannot reduce that. Don't cancel the 3, by the way. And then let's apply the natural lorem on both sides. If we apply the natural lorem on both sides, so we have the natural lorem of 3 divided by 23 equal to the natural lorem of 13 over 23 divided by 3, and then the time. Okay, so the time is equal to what? The time is equal to 3 times the natural log of 3 over 23 divided by the natural log of 13 divided by 23. Okay, so if we use the calculator, then what I know so far is that it should be bigger than 5. Okay, let's see if that is true. Okay, so the result here is 10 minutes. So here the result is 10.7 minutes. So it makes sense, it's bigger than 5 minutes. And here it takes very long time because the difference is becoming, is smaller, the difference between the current temperature and the ambient temperature. Remember that the rate or the speed is going to decrease when you get closer to the ambient temperature. So reaching to the ambient temperature is going to take more time. Okay, so we have answer A and B. Now, inciso C is a very tricky question, because if you replace here the value of 70, which is very similar to inciso A, they are giving you the temperature, then you have to calculate the time. Now imagine that you replace here 70. So 70 and 70, they cancel, is equal to 0. So that means that here you will have 0 here. That means that you will have the natural log of 0, and the natural log of 0 doesn't exist. So why it doesn't exist? Okay, the time to get when the temperature will get 70 degrees, that is in the infinite, because the ambient temperature is an asymptote. So the answer for inciso C is that the temperature T when T tends to infinite is equal to 70 degrees Fahrenheit. So the answer is T equal to infinite. Alright? So you will need to wait years so that the temperature will get to 70 degrees. Now that is in mathematical theory. In reality, you just have to wait like 20 or half an hour to reach 70 degrees. The cake temperature will be like 70.001 degrees Fahrenheit. Well, for us it's already 70 degrees Fahrenheit. But mathematically it will never reach 70 degrees, right? It's going to be just a little bit higher, but only on the infinite. But that is mathematically. In reality, thinking as engineers is just wait very long time. Alright? Okay, so this is an example of cooling and warming differential equation model. On the next video we are going to do mixtures problems, and that will be the last model of the applications, and then it will be the last of the unit. Okay, see you in the next video.